Journey beyond reality. How time and mathematics dance in the fifth, sixth, and seventh dimensions. Embarking on a cosmic adventure. What if reality stretched far beyond the world we know? Picture yourself soaring past the familiar three dimensions of space, length, width, height, and the relentless march of time. In our everyday lives, we're bound by this four-dimensional cage, where time ticks forward and math maps out the rules of gravity, motion, and light. But what happens when we leap into the fifth, sixth, and seventh dimensions? Buckle up for a mind-bending ride through realms where time twists, bends, and even vanishes, and mathematics morphs into dazzling new forms. Drawing from the wild frontiers of string theory, M-theory, and cosmic imagination, this essay explores how time and math might behave in these higher dimensions, with vivid examples to light the way. Let's dive into the unknown. Setting the stage, our four-dimensional playground. Before we blast off, let's ground ourselves. We live in a four-dimensional universe. Three spatial dimensions let us roam up, down, left, or right, while time drags us forward through moments of joy, sorrow, and everything in between. Einstein's general relativity paints this as a smooth, four-dimensional canvas, with a metric tensor, weaving space and time into a curved tapestry. Our math, Euclidean geometry, calculus, and more, helps us navigate this world, from plotting a rocket's path to predicting a storm. But theoretical physics whispers of more. String theory dreams of tiny, curled-up dimensions, invisible at scales smaller than a billionth of a meter. Others, like Bryn world cosmology, imagine vast, unseen realms. For this adventure, we'll assume these higher dimensions are open to exploration, letting us ponder how time and math transform in the fifth, sixth, and seventh dimensions. Ready? Let's go. The fifth dimension. Time as a cosmic highway. Time's wild new groove. Step into the fifth dimension, and time stops being a one-way street. Imagine it as a sprawling highway system, where each lane is a different timeline, a parallel universe with its own version of history. Inspired by Kaluza-Klein theory, which once tried to fuse gravity and electromagnetism in a fifth dimension, we picture time as a vast plane. Every point on this plane is a moment in a specific reality, and you can swerve between them like a cosmic driver. Think of it like a choose-your-own-adventure book with infinite pages. In one lane, dinosaurs still roam Earth. In another, you're sipping coffee on Mars in 2025. A fifth-dimensional traveler could hop between these realities, witnessing alternate versions of your life, maybe one where you became a rock star instead of an accountant. Time isn't just forward or backward, it's sideways, too, weaving a web of interconnected stories. Causality gets messy here, as events in one timeline might ripple into others, like a pebble tossed into a pond, creating waves of change across realities. Picture this. You're in a fifth-dimensional cafe, watching two versions of a historical event, like the moon landing, play out differently. In one timeline, it sparks a global space race. In another, it's a hoax that fuels distrust. You could even loop back to revisit a moment or jump to a future where humanity colonizes the stars. Time becomes a playground, not a prison. Mathematics. Mapping the cosmic highway. To navigate this time plane, math gets a serious upgrade. In our world, general relativity uses a 4x4 matrix called the metric tensor to describe spacetime's curves. In the fifth dimension, it's a 5x5 matrix, with an extra coordinate for switching timelines. Imagine a formula like ds squared equals c squared dt squared plus dx squared plus di squared plus dz squared plus dw squared. Here, w is your ticket to alternate realities, measuring distances across timelines. Math also gets probabilistic. You'd need a new kind of statistics to predict how timelines split, say, after a quantum coin flip or a major historical choice. Picture a Timeline divergence equation, tracking how one reality branches into many, like a tree sprouting endless limbs. For example, if Schrödinger's cat lives in one timeline and dies in another, fifth-dimensional math might calculate the odds of each outcome influencing nearby realities. Topology, the study of shapes, becomes your GPS. Five-dimensional shapes, like the Calabi-Yau manifolds from string theory, could map this time plane's twists and turns. Imagine a topological knot, representing a cluster of similar timelines, with equations entangling how they connect. Math here isn't just numbers, it's a cosmic roadmap. The sixth dimension. Time as a galactic library. Time's grand tapestry. Now, let's soar to the sixth dimension, where time becomes a breathtaking library of every possible story your universe could tell. Imagine a vast archive where each book is a complete timeline, from the Big Bang to the universe's final fade. This is the phase space, a concept borrowed from physics where every point captures a possible state of the system. Here, every point is an entire history, every choice, every quantum quirk. Time doesn't flow anymore, it's a frozen masterpiece. You're not stuck in one story but can wander through every possible version of your universe. Picture standing in this library, flipping through timelines. One where Earth is a lush paradise, another where it's a barren wasteland. A sixth dimensional you could see every outcome of your life, every career, every love, every mistake, laid out like pages in a book. Navigation here means picking a timeline to explore, like choosing a movie from an infinite streaming service. Causality isn't a chain of events but a network of connections between these histories. Time becomes a parameter, a way to label each book in the library, not a relentless march forward. Mathematics. Cataloging the infinite. Math in the sixth dimension is a librarian's dream. You'd need set theory on steroids to handle the infinite collection of timelines. Each set might represent a universe's possible histories, with some sets vaster than others. For example, a universe with strict physical laws might have fewer possible timelines than one with chaotic rules, and math would quantify this difference. Geometry gets wilder. Six-dimensional manifolds describe the shape of this phase space, with curvature revealing how timelines cluster. Imagine a region where timelines are tightly packed, like books on a shelf, representing similar histories, say, universes where humans invent AI. A mathematical tool like the Ricci curvature tensor, r_mu nu equals partial underscore lambda gamma caret lambda underscore mu nu partial underscore nu gamma caret lambda underscore mu lambda plus gamma caret lambda underscore sigma lambda gamma caret sigma underscore mu nu gamma caret lambda underscore sigma nu gamma caret sigma underscore mu lambda could measure how these timelines curve around each other. Probability evolves into a possibility calculus. Instead of odds for single events, you'd calculate the density of certain histories in the phase space. Think of a wave function for entire timelines. I h bar frac partial psi partial w equals hat h underscore 6 psi, where psi assigns amplitudes to whole universes, and w navigates the sixth dimension. Group theory might reveal symmetries, like transformations that leave certain timelines unchanged, helping you spot patterns in the cosmic library. The seventh dimension. Time beyond the multiverse. Time's ultimate frontier. Hold on tight. We're entering the seventh dimension, where time becomes a cosmic symphony of every possible universe. Picture a multiverse where each universe has its own physical laws, constants, and even definitions of time. M-theory, with its 11-dimensional dreams, inspires this vision. Here, time isn't just a property of one universe but a meta-rule governing how universes relate. Imagine a seventh-dimensional gallery, where each exhibit is a universe with its own physics. In one, time flows backward. In another, it's a looping cycle. In a third, it's a frozen instant. A seventh-dimensional traveler could stroll between these, experiencing realities where gravity repels, light crawls, or time doesn't exist at all. Time becomes a lens for comparing these universes, like a universal translator for cosmic rules. For example, you might step from our universe, where time is linear and the speed of light is 299,792,458 meters per second, into one where time is quantized, ticking in discrete steps. The seventh dimension lets you see time as a variable, not a constant, reshaping how you perceive reality itself. Mathematics, the language of everything. Math in the seventh dimension is a mind-blowing metamathematics. Each universe might have its own mathematical system. Ours uses calculus and geometry, but another might rely on fractal logic or something unimaginable. Category theory becomes your guide, mapping relationships between these systems. Picture a functor linking Newton's F equals ma in our universe to F equals m squared a cubed in another, preserving the idea of force while adapting to new rules. Algebraic topology could sketch the multiverse's structure. Imagine a seventh-dimensional shape, where universes are connected like bubbles in a foam, with homotopy groups revealing how they link. For instance, two universes with similar physical constants might be adjacent, accessible through a seventh-dimensional path. Infinity itself gets redefined. The seventh dimension might hold a hierarchy of infinities, each tied to a different multiverse. Transfinite numbers could count the number of possible universes, with equations like Aleph_1 equals text. Universes with linear time, quantifying entire cosmological categories. Math here isn't just a tool, it's the blueprint of existence. Why this matters? A cosmic wake-up call. This journey isn't just a thought experiment, it shakes the foundations of reality. If time is navigable, is free will just a choice among infinite paths? If math varies across universes, is it a universal truth or a local dialect? These questions echo ancient philosophical debates, from Plato's eternal forms to Kant's constructed reality, but higher dimensions give them new life. Practically, these ideas could spark breakthroughs. Fifth-dimensional math might unlock secrets of quantum entanglement across timelines, while seventh-dimensional models could unify quantum mechanics and relativity by finding universal patterns. Even if we can't visit these dimensions, imagining them pushes our science forward, just as non-Euclidean geometry once paved the way for Einstein. The catch: our human limits. Here's the rub. Our brains are wired for 4 dimensions. Visualizing a fifth-dimensional time plane is like a flatlander grasping 3D space, tough, but not impossible with analogies. The math we need might require axioms we haven't dreamed up yet, and detecting higher dimensions is a long shot with today's tech. String theory's tiny dimensions are still theoretical, and extended dimensions might be beyond our reach. But dreaming big has always driven discovery. Think of Galileo gazing at the stars. Conclusion: a universe of possibilities. In the fifth dimension, time becomes a cosmic highway, with math mapping infinite timelines. In the sixth, it's a galactic library of every possible story, with equations cataloging endless histories. In the seventh, time transcends into a symphony of universes, with metamathematics weaving their rules together. This journey through higher dimensions isn't just a flight of fancy ascent to the fifth dimension, where time and math dance in wild, wondrous ways. As we imagine these realms, we're not just exploring ideas, we're rewriting the story of reality itself. Let's keep dreaming, calculating, and venturing into the unknown.